Hi, I'm Joe Laughlin from the Windows Performance team, and this video is about understanding heap usage using the Windows Performance Analyzer. So here's the agenda for this video. First, we're going to go over some heap overview and concepts. Then we're going to do a demo on collecting and analyzing heap data. Then, once we're done with the demo, we're going to talk about some guidelines and best practices to keep in mind regarding the heap. And then we're going to finish up with some key takeaways. So let's do the overview. Okay, the Windows heap is used to handle dynamically allocated data within the process. The Windows heap has three basic allocation areas. The main line, or NT heap, which is where allocations will be placed until certain allocation count thresholds are reached. Once those allocation count thresholds are reached on a per allocation size basis, subsequent allocations will be placed within the low fragmentation heap. The low fragmentation heap uses subsegments, which you can think of as chunks of blocks all of the same size. For example, we might have a subsegment that contains 100 8-byte blocks. However, you need to keep in mind that the heap does not service all dynamic allocations, even when you're using the heap APIs or using things like new. If the allocation is over 64K in size, the allocation will be passed to the virtual alloc APIs and be handled there. So, the heap is used, as I said earlier, for dynamic allocations. And these allocations can be made by either calling the Win32 heap APIs directly or by things like the C and C+ allocators, new, alloc, realloc, and calloc. And it's very important for application developers to understand how their process is using the heap so that they can understand the memory usage for their process. So there's a number of key concepts that we need to mention at this point. The low fragmentation heap, as I mentioned earlier, it's used once allocation thresholds are met, and the low fragmentation heap is available and used on all Windows processes in Vista, Win 7, and in Win 8. The next concept is subsegment, which is a chunk of LFH bucket sizes. So I mentioned earlier that we could have 100 8-byte blocks in a subsegment. Subsegments increase in size as the number of outstanding allocations of a given bucket size increase. So if you have 1,000 8-byte allocations in your heap, the next subsegment you create is going to be bigger than the one that you created previously. And they increase in reasonable size chunks, but it's something you need to be conscious of. The other big concept is fragmentation. Fragmentation is caused in a large part by intermingling allocations of differing lifetimes. So if I allocate a few things that are going to be short-lived, and then some things that are going to be long-lived, and then some more things that are short-lived, some things that are long-lived, and then I free up all my short-lived things, I'm going to keep alive all the subsegments that the long-lived allocations reside within. If I allocate enough transient things that live long enough that I place my long-lived allocations in a number of subsegments, you can see how this can impact the memory usage of the process in significant ways. So lifetime is a very important concept to keep in mind. So let's talk about how we do heap data collection and analysis using WPA. First thing is we need to go over some basic vocabulary so you can understand how the data is going to be presented within the tools. Every heap allocation has some basic data associated with it. How long it lives, the stack that was used to allocate, the address that the allocation was placed at, the page within which that address resides, and some information about the low fragmentation heap bucket size that allocation was placed within. So the LFH bucket sizes are somewhat granular, but not completely granular. So, for example, the LFH 8-byte bucket size will be used to handle allocations for things between 1 byte in size and 8 byte in size. And then there are a number of LFH bucket sizes, some of which handle allocations 8K, 16K, etc. in size. And again, each bucket covers a range of size. The larger buckets have larger ranges of sizes they handle. So you need to be conscious if you go from a smaller bucket size to a larger bucket size. You may want to consider things like, if I can reduce the size of my allocation by just a few bytes, I can end up in a smaller bucket and hence in a subsegment that was allocated for other purposes. The other thing to keep in mind is that if only a limited number of allocations end up in these larger bucket sizes, I may have, a subsegment that's capable of holding, for example, 58K chunks. Right? But if I only allocate, a handful of things, I'm ending up with a lot of wastage there. So you need to be conscious of that, and the tools will tell you, and the data you collect will tell you when those types of issues are present in your process. There's also a bunch of metadata that's present in the summary tables inside WPA. For example, the number of slots that are available within a subsegment. We also need to talk about things like heap overhead. So on 32-bit processes, for every heap allocation you make, there's 8 bytes of overhead that is used by the heap manager to keep track of the allocations. On 64-bit processes, each allocation has 16 bytes of overhead. So if you have a large number of allocations, the overhead adds up. And so you should keep that in mind and maybe do other things to consolidate some of your data structures into things like an array. You can allocate an array of data structures, and therefore you're only going to pay the overhead once, even though your array contains n items. That will increase code complexity in your application, so you need to make some trade-offs against code complexity and memory usage, which only the application developer can do. Also, for every heap allocation, there's also a bunch of context data that enables us to understand whether or not an allocation is transient or outstanding at any given point in time. So let's talk about how we do data collection for the heap using Windows Performance Recorder UI. Heap allocation data is process specific, so we have to select a process in WPR UI to be able to collect the data. And we also have to select, in this case, that we want to collect heap data. Once you've selected these two things, click on Start, repro the scenario of interest within the process that you've just launched. When you're done, click on Save to save the trace, which we can open later in WPA for analysis. In WPA, there's going to be a number of heap graphs. Heap data is rather complex, and to help simplify our understanding about what's going on, we have different ways to represent that data graphically. There's actually 8 graphs, 2 graphs around outstanding allocation size and count, 2 graphs around total allocation size and count, and then we also have 3 graphs that give you more details about low fragmentation heap behavior, one that shows you the total number of outstanding allocation slots, so in other words, the number of subsegments we have times the size of those subsegments, the number of unused slots within those subsegments by count, and then the number of unused slots within those subsegments by size. And last but not least, there's the heap extents graph, which includes all of the heap overhead, both from a per allocation perspective, from a per subsegment perspective, and also additional data structures that the heap manager allocates to track information in the heap. And within the summary table itself, we're going to express the context data that we talked about earlier to show you when allocations are allocated and freed using these 4-letter acronyms shown on the slide. So let's move on to the demo. So in the interest of time, I'm starting with a trace that is opened, and I've already loaded symbols and spent some time making sure symbols are resolved so that we don't have delays for symbol resolution in the demo. The view that I've brought over here is the outstanding size of the heap plotted versus time. Each one of the lines in the graph shows a different heap. So you can see here that there are a number of heaps, about 8. Each one of these lines, like I said, corresponds to a heap. There are 2 processes here because IE is composed of 2 processes, a frame and a tab process. And this trace is also from Windows 7 to show you some of the types of issues that have been addressed since then. So here you can see some interesting things that happen in the graph. Here this heap has a huge increase in the amount of outstanding allocations. Again, this is by size. So we've increased dramatically here in size. We have other heaps that are showing not quite as dramatic increase, but an increase. So this is an interesting area of the trace to drill into. Over here is where we freed some things and then allocated some more. In this particular heap here with the blue line, though, we freed a lot and then we start allocating again later. So we might be interested to see what we freed here. And in these other heaps, there's a number of different humps, all of which would be interesting. So let's pick one of these areas. So let's pick something here. And now in the summary table below, the things that were allocated in there are going to be highlighted in the summary table. So if I drill in to this particular IE process, which is the tab process, we can see that we have a large number of allocations, and in this case, this line probably corresponds to this heap, which is indicated by this heap handle, and we have 341,000 allocations that happened there. If I open the heap, I can see that there were a large number of transient allocations as indicated by the 4-letter acronym AIFI, and there are about 61,000 allocations that are still alive at the end of my view over here. Those 61,000 allocations still, however, account for about 7 megabytes. So let's drill into what's going on here. And we can continue to drill into the trace, and we'll eventually end up all the way down at the bottom at one of the heap allocation APIs, RTL allocate heap, which was called as a consequence of IE allocating memory. So there's a bunch of columns here that I can bring into view because the stack was so deep, some of them got scrunched. So we talked about the LFH bucket. So if I move this over here to the left of the stack column and then reopen the outstanding allocations, you can see the different LFH bucket sizes that were used. I can sort by bucket size, and this gives you the bucket number but also the range of allocations that were serviced by this bucket. You can see here we have a large, about 6,000 outstanding allocations that fit into this bucket, about 8,000 in the next larger bucket, and you can see that the bucket sizes increase and the range of the allocation services serviced by those buckets also increases. So for example, you can see here for this bucket size we have 1 outstanding allocation. And you can see where that allocation was made, and it was for a buffer that was used for networking purposes. So this gives you an idea how to drill into things. And this is just the outstanding summary table graph, and the outstanding graph and the corresponding summary table. So there are other graphs and other summary tables that expose additional information, such as more details about the LFH, the number of outstanding subsegments, the number of slots available in those subsegments, that I would encourage you to explore so you can understand how your allocation patterns impact the heap usage of your process. So now that we're done with the demo, let's go over the guidelines and best practices. The most important thing is to understand how dynamic memory allocations impact the heap usage of your process, particularly how transient and outstanding or long-lived or steady-state allocations interact with each other to account for your memory usage. In general, the guidance is to reduce both the number and size of outstanding allocations and reduce the number of subsegments that you create, particularly if you create a large number of subsegments that end up only partially filled. The way to reduce the number of subsegments that get allocated is to reduce the total number of allocations that are made within the process, or potentially by reducing the number of heaps that you create. Again, it's very important to avoid intermingling long-lived allocations with short-lived ones, because that can lead to fragmentation and keeping alive a large number of subsegments that are only partially used. So the key takeaways are, again, to understand how heap allocations and your heap allocation patterns impact the heap usage of your process, understand the concepts of the low fragmentation heap, subsegments, and how allocation patterns impact fragmentation, particularly the intermingling of long-lived and short-lived allocations, and to use the tools to understand the heap usage of your component and identify areas for optimization.